Why does this sound different from this? Or this?
Well, before we answer that, we first have to define what this is. And in this case, it's pitch. We're going to start with the most basic object in sound, which is vibration. When I refer to a vibration, I'm going to mean an oscillation that repeats the same pattern over and over, like a point moving up and down. If the pattern repeats every p seconds, we would call p the period, and the frequency, which is the number of repetitions per second, is equal to 1 over the period. Now that we have a good definition of frequency, we can define what pitch is. So musical tones result from a vibration transmitted through the air as a sound wave, and the pitch of that said tone is the frequency of that vibration which is measured. One interesting thing that the ancient Greeks discovered is that the relationship between two pitches can be expressed by the ratio of the frequencies. For example, the octave is literally a 2-to-1 ratio of the frequencies, as you need to double the frequency to get to it. So now let's create the full set of pitches used in Western music. To do this, we divide the simple 2-to-1 ratio we looked at earlier into 12 steps called semitones. Let's define a real number, let's say z, and if z is done 12 times, it will give an octave, and we can set z to the 12th equal to 2. So for any interval of n semitones, we can get the ratio from putting the number of semitones in the numerator of our equation. So far, we've been acting like a note is a single frequency, but real musical sounds aren't single frequency waves. If they were, then a violin would sound the same as a piano playing the same note. So if two instruments play the same pitch, the same F, they can still sound totally different. This is called timbre. And once we accept that the vibration is a periodic function, you can ask how the shape of f of t creates the character of the sound. Back to Pythagoras. Another thing that the Greeks noticed was that a string doesn't just vibrate at a single frequency. Mathematicians later formalized this to prove that this series is ordered. A string vibrates at many frequencies that are stacked precisely in something called the overtone series. To understand this, we have to do some basic Fourier analysis. Fourier theory says that roughly, that any well-behaved periodic function can be expressed as a sum of sine and cosine waves. So if g of t has period p, then it can be built from frequencies f, 2f, 3f, 4f. In other words, integer multiples of the fundamental frequency. One way to write that is as an infinite sum, right here. Each term corresponds to a component at frequency kf. These components are what are called harmonics, overtones if you will. The overtone series naturally contains frequencies in integer ratios. Those are exactly the same as the ratios that generate consonant intervals. Pretty cool, right?